Okay, so let's have one proof of this general thing. So see the proof that this is really satisfies in general this curly G with these projection maps, satisfies these conditions 1 and 2 here. So as in the definitions, we have 2 conditions to check. Because it's so general, it is all quite easy, but let us see how it works. So first one, of course, if we have curly G, here some Gj, Gi, I smaller or equal than G, then we have to see whether it is commutative, but here we have this this sequence of coordinates having this property, and actually this property exactly says that this diagram is commutative. So here we have, let's say, Gn, and in I, by this map, this goes to the ith coordinate, to jth coordinate. By this map, this goes to Rji of Gj, and by this map, it goes to Gi, and it is equal by definition. So this works. And for second, this just takes more if we have this another candidate. H together with the maps Ti to Gi such that this diagram holds, is commutative. Then we have to, first, we have to define a map from H to G like this, and then say that that there is only one such a map. Okay, so define phi to this curly J by phi of H as the sequence of all images of the Tj's, or Ti's. And so far it is just here, but because this diagram commutes, it exactly says that this is in this curly G. Yes, so it is Tjh by Rji goes to Tih. That's exactly what it says. So really this map phi goes to from H to curly G, and it's a homomorphism. Well, and then uniqueness is also pretty obvious. So Okay, now. So if we have another H, okay, sorry, I didn't still checked. I haven't checked that this property is satisfied. Okay, but this is again, but still okay. So now take I in I. We have to check whether it is commutative. But if we start from H here, this goes to phi H, which by definition is this. So here, by the projection on ith coordinate, this must go to Tij, to Ti of H, and by definition this is also Ti of H. So okay, so now we are at this moment that there is such a phi such that this map, this homomorphism, such that always this diagram commutes, and now uniqueness finally of such a phi. So if we have or any other phi prime, such that again this commutes, we have that, so since this is a projection, then this says phi prime, we have the ith coordinate of phi prime H, which is Ri of phi prime H, equals Ti of H. So phi prime of H equals this, equals E of H. Okay, so everything is just pretty direct checking, but let's do it once. Okay, so this is the argument. It always exists, and it always, okay, sometimes it doesn't immediately looks like this, but it may be taken in such a presentation. So now let's see some more examples of inverse systems coming from arbitrary groups. And then finally we will see p-adics, or rather q-adics. it's quite a general example of profinite completion of a group. So now we start from G. Okay. It will not be like this. G is just any group. And from any group, we produce inverse system of finite groups. So first, let G be a enumeration of all normal subgroups of finite index. Okay, we can do that. So now, so again, let us say that I is smaller or equal than J, if and only if Gi is a subgroup of Gj. So now we get inverse system of quotients. Then
is it possible to put an order like that?
yes. I mean, always when you have sets, subsets of a set, they are ordered partially by inclusion.
But lots of them may not be a chain.
Not a chain, so it's not necessarily a chain. I will see examples soon in Z what happens. But that was always, it was never a chain almost. Like in these finite fields, it was also not a chain. Yes. So the order is not linear, it's a partial order.
So every chain of them are ordered by the primes, right? So
Sorry?
every chain of them, every chain of the normal subgroups are ordered by the primes then.
In Z or in where?
So you say that, okay.
So, okay, I will see. So this is an inverse system of finite groups. Yes, because if Ga is a subgroup of Gj, am I saying the right thing? Then what maps to what?
Is it, I think,
The opposite, perhaps. Because then I want to map G. No, good. The smaller. So it's not inverse now. Okay. Okay, I missed that point. I think here I want it like this. Maybe that was better. Better. Okay, then.
There might be infinitely many normal subgroups which are indexed too.
Yes. Okay, so kind of in the, they may go down. But that's the, okay, let me now see if this is right. So, okay. So I want it to be inverse system. So if I is smaller than J, that means that Gj, okay, that Gi or Gj am I getting? Okay, and that means that if I divide by a smaller one, then here I have kind of quotient map. Yes. If I divide by smaller, then I have a map like quotient division to the quotient by a bigger. Like if I divide by nothing here, by trivial group, then I have quotient map to the G over GA. Okay, so this confused me.
But I'm not still
Okay.
sure that you can put such an order on normal subgroups.
Okay, so that I'm saying that if you have any family of subsets of some set, it's always ordered by inclusion or reverse inclusion.
You are taking group G
Yes.
as in a manner that you can put such an order. So G
I mean, this is also just really inclusion here.
No, I get it, but this puts and this transforms normal subgroups into a chain.
Not necessarily a chain.
Because there might be a G1, and G1 contains all of them, and G2. G2 is in G1, and G2 contains all of them, G3, G4, like that.
But for example, let us see practical example. If G is Z,
Yes.
then my GI is I times Z.
Okay.
Okay, and then
G2 does not contain G3.
yes, but it's still an order. But it's a partial order. So it's again like divisibility order. It's not a total order, but it's a partial order.
But G2 does not contain G3.
Yes.
But 2 is smaller than 3.
No. No.
What do you mean by that?
In this, with respect to this relation, no.
Sıralama onunla tanımlanıyor. This is the definition of the order, right?
Tamam, şimdi diyor ki 2z'de, şimdi bunun tanımına göre 2 3'ten küçük, demek ki 2z 2z'de içermeli o zaman.
Değil, 2-3'ten küçük değil.
Sayı olarak 2 3'ten küçük değil mi?
O başka sıralama, buradaki başka sıralama.
Depends what you mean by kuchuk. Kuchuk with respect to standard order, yes. But with respect to this order, it becomes divisibility order, as before. So we may finish it. So, okay, so when Iz belongs to Jz. Yes, if and only if now I'm not confused, I think, I divides J. Or the other way. J divides I. Yes, because this is like one. J divides I. So this is my order on N now. Divisibility. By definition. It was like this at the beginning, okay? The same was with this FPI. The same, FP square is not contained in FP cube, but 2 is smaller than 3, but not in this sense.
Okay,
Yeah.
I thought that you're taking cardinal order.
No, I'm defining always order. I'm defining order, as in the beginning, okay? Okay, so yes, by definition. So this example, okay, so what is here? Okay, so for example, this. Okay, so I have this inverse system. So now the definition is really G hat, by definition, is the inverse limit of this system. So system. And this is called profinite completion.
What is completion with the finite case?
Huh?
If G is finite, what's this?
You usually ask something very nicely, which is my first example after the definition. Which means that it's natural question. Yes, it's the same. Nothing changes. Yes, because then you have, okay, now maximal or minimal your inverse system just stops. Because there is a biggest or smallest, there is this here smallest subgroup of finite index, which is just trivial subgroup, which is in this sense the largest element in this order, and then always inverse system is just element from this largest element, from this largest point in the order. Yes, because you go kind of up, 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 but if there is a limit point, you stop there. Okay, of G. So now I have particular examples, exactly. Examples. G finite. G hat equals G. So not interesting. Then. This will be problem 2. If G equals Z, then problem 8. Then kind of it's this inverse system here from Z is the same like this inverse system of all finite cyclic groups. So the inverse limit is also the same. So divisibility relation. So it's just comparing that, which we almost discussed here, that the inverse system we obtain from Z by this procedure is the same as described before for finite cyclic groups. So the limits must be the same as well. Okay. So this is inverse system of all finite cyclic groups. But then, thanks to that, this is our absolute Galois group of Fp. Because we noticed before that this inverse system was also inverse system of Galois groups of Fpi over Fp. So all these three things coincide. Huh?
So we will find what is this inverse.
Yes. Well, we are close. Not much more can be said than that. But okay, but something can be said. Okay, but I'm just saying, so Z hat this group is also okay. Never mind. Yeah, for all, of course. So you see this side doesn't depend on any prime. And then problem... Okay, didn't I should have said something before, but let Q be a prime and ZQ be the inverse limit of this part of this system when I is Q, is just power of Q. Yes, this was also discussed before. So this is called I'm saying Q to distinguish from this P which was fixed here, Q addix, actually, additive. Because there are also rings, so you can take inverse system of rings with multiplication, zqi, z over qiz, then this becomes profinite ring, and this is the ring of Q addix. But with this description, this is the additive part. So problem 9 says which is quite natural, this is like Q part of this system, and actually Z hat, that refers to your first guess. Yes, so this is not P addix or Q addix, but it's the product of all of them. Infinite product of all this ZQ. So sometimes also people write this as for group of Q elements, but now it's very different. It's Q addix, so it's in particular uncountable. So that's the result. Okay, if you count, you can represent this as infinite product of this. So in a way, yes, you have P addix, Q addix here, but all of them are all possible. Again, unrelated to the P we started from. So it's quite a big, okay, if you think. Yeah, so you may think it's quite a big group, even if it's kind of topologically, it's called procyclic because, there was no topology yet, sorry. It's kind of cyclic group in certain sense. And then 3, so this was big. Okay, so maybe you have a guess. Q plus, of course. What is Q hat?
There is no finite index.
Yes, so there is one.
Q is.
Yes.
Okay. So, Q.
No, the quotients. It comes from quotients.
No, trivial one.
It's 0.
Zero.
Yeah. So it doesn't have to be big. Okay. So always we have this, yes, because as you said, because Q is divisible, so no proper finite index subgroups. So divisible groups have trivial completions. Okay, then the completion actually suggests there should be some connection with G, and there is. So there is always a map. Okay, so actually from the universal part of the definition of inverse limit, so for each I, there is a map G over, okay, let's say Ij, just quotient map, another quotient here, and it commutes with the map from the system. So from universality in definition of inverse limit, there is a unique map homomorphism. So this is how you can find G inside G hat. Okay? And then we will see that with the natural topology, this G is dense, the image is dense. So in this sense, it makes sense, say it's a completion. Okay. But we have no topology yet. And okay, so how much? Okay. This may stay. Okay, so the point is that this gal mk, as we noticed, is determined by this system I write it, but the group structure here is not enough for the Galois correspondence. So we need more structure. Okay. And this determining will help to more structure, so in short, we need topology. And this topology tells us which subgroups are good, which subgroups should be in Galois correspondence. So which subgroups really corresponds to subfields. Okay? And they will be exactly the closed subgroups. Okay, so have here a remark that it's kind of general situation that if you talk about infinite groups, usually to understand them well, it's not enough to look only at the algebraic structure. There should be something more like Lie group, topological group, algebraic group, some extra structure. For finite ones, okay, from purely algebraic structure, usually everything can be understood. But to understand infinite ones, in practice, usually something more is necessary. And it really happens here that this one comes with natural topology, and only with this topology it can be properly understood. Okay, so for this topology, we need to first understand topology here. So some general topology a little bit. We have a system. Now this is not ordered for a moment. This is topological spaces. So now the product is also topological space with so-called Tikhonov topology. So I'm not sure, probably you know for finite products, I'm not sure about infinite products, what is a good topology on infinite product of topological spaces. So it's a bit like a direct sum of infinitely many groups, that everywhere it should be something trivial. Here something trivial is everything. So basis.
The main idea is making.
Huh?
The main idea is making projections.
Yes, that's my comment in 2 minutes. So basis. Consists of such that each of them is open, and for almost all I, it's just everything. So, okay, so of course in the finite one, the basis is the squares, but for infinite it's a bit hard to imagine, but almost everywhere everything, but on finitely many things like this. So as you said, this is coarsest or smallest topology such that all projections are continuous. Okay, and a bit maybe surprising Tikhonov theorem. It's surprising because compactness is about finite things, and this theorem says that any product of compact spaces is compact. So if all Ti are compact, then product is compact. So in our case, we took this finite. Now we look at finite GIs. Okay, our case, we have G, okay, let's say in this form, where GI is finite, then GI is compact with discrete topology. Everything is open. So, by Tikhonov theorem, this product is also compact. And now, okay, so maybe the main theorem will be next time, but the main theorem is that this is closed subset in this topological space, so it becomes also compact. So our Galois group will become compact topological group with this topology. And with this structure, we get the fundamental theorem of infinite Galois theory. So just at the end, okay, probably you know it, I wanted to give, so there are strange spaces, these products, but somehow they still exist in nature. So I wanted to give the example of Cantor set, which you probably know.
We didn't show, but we should
Huh?
show that the operations are continuous, right?
Yes, that comes later, but I didn't say formally what is topological group yet. So that will be on Sunday, yes, yes, of course. And inverse. So Cantor set which should be also the same as actually p-adix, yes, topologically. So this is this idea. We have 0, 1, and then we remove so and from here you also remove the middle. And so on. So like C0 is 0, 1, C1 is 0, 1, 3, 2, 3, 1. And then if we have Cn, so it's the same as 1 over 3 times C0 plus 2/3 plus this. And if we continue like this, Cn plus 1, the same operation applied to Cn. And this Cantor set is, because we continue, is intersection of all of this. So this is topological space just with the induced topology. From R or 0, 1, and okay, it's like consisting only of holes, kind of, but it's still compact. We intersect, it's a closed set in 0, 1, and actually it turns out that this is homeomorphic. Okay, just if here we always take 0, 1. In other words, a product okay, I not say, but so the point is that these strange topological spaces can be even found in a very classically inside our normal real line in such a strange way. So kind of they exist more than one could think in reality. Okay, thanks. Maybe time.